We are seeing optical communication and here we are dealing with optical sources. What are the optical sources we are seeing is laser diodes and LED. So here in optical communication system we require bandwidth which are greater than 200 megahertz. So if you take different types of optical sources, we have laser diode. What are the important characteristics in laser diode is its response time is less than 1 nanosecond, then optical bandwidth is less than 2 nanometer or equal to 2 nanometer. Coupling with several tens of milliwatts of power into optical fiber. Then the mode field diameter is very small and it uses multi-layered heterojunction devices. If you take LED as a source, optical source, we can have a double heterojunction to achieve the optical confinement and carrier confinement. If we use LED as an optical source, it is simple and we can have very small temperature dependence of emitted optical power and there is no catastrophic degradation if we use LED source. Then we have laser. If you take laser, the construction is more somewhat complicated and we have to do current confinement. In addition to that, if we take an LED, the output will be incoherent. There will be no optical cavity. So output radiation, if you see, means the spectral width will be very broad. If you take laser, the output will be coherent. So for that only we are using laser. The coherent source, since how we are obtaining the coherent source is due to the optical resonant cavity. It is highly monochromatic and the output beam is very directional. So choosing the optical source, there are different, it depends on the characteristics of optical fiber, some such as geometry, attenuation as a function of wavelength, then group delay distortion, modal characteristics. So these characteristics we have to take into account while deciding the optical source. So if we take laser, we can use single or multi-mode fiber. If we take LED as a optical source, we should use only multi-mode fiber. So if you see what is carrier confinement and optical confinement, carrier confinement used to achieve a high level of radiative recombination, so we can get a high quantum efficiency. Optical confinement it is possible because we can prevent the absorption of the emitter radiation by the material surrounding the PN junction. So if we say we are taking LED configuration, we can use homo junctions and single and double heterojunction. So here mostly double hetero structure is used. They are made up of two different alloy layers on each side of the active region. If we take dual confinement, it will result in high efficiency and high rates. So if we take LED as the optical source, one of the advantages we have is the data rate is 100 to 200 megabits per second with multimode fiber and the power will be tens of microwatts. So if we take choose LED as the optical source, it is the best choice because it is very simple, it is less complex and no thermal or optical stabilization. So because of this LED source, we have high radiance output, then fast emission response time and high quantum efficiency. And in addition to that, we have the equilibrium condition and the total rate, that is carriers generated, will be equal to externally supplied plus thermally generated rates. The current density J by QD is the externally supplied carriers. So J is the current density, Q is the electron charge, D is the thickness of the recombination region. So N by tau is the thermal generation rate. So we can write the rate equation as dN by dt equal to J by QD minus N by tau. So the equilibrium condition is N is equal to J tau by QD. In addition to that, if we see the frequency response of LED, it depends on the doping level in the active region, the injected carrier lifetime in the recombination region, that is tau I, then the parasitic capacitance of the LED. So if the drive current of an LED is modulated at a frequency of omega, the output optical power of the device will vary as this function. P of omega is equal to P naught divided by root of 1 plus omega tau the whole square. So the electrical current is directly proportional to the optical power. So thus we can define the electrical bandwidth and optical bandwidth separately by this formula. Electrical bandwidth is equal to 10 log of P of omega divided by P of 0. So that is P of omega will be the input power, P of 0 will be the output power, or you can write it as 20 log of the current, output current divided by the input current, I of omega divided by the I of O. So P is the electrical power, I is the electrical. So if we choose the optical source as a laser diode, what and all advantages we have is the basic requirement of laser diodes we are seeing here. So here the optical and carrier confinement between heterojunction layers we will observe, and the current flow will be restricted laterally to a narrow stripe along the length of the laser. So to achieve this, many methods are proposed, but most of the methods are limiting because of the lateral modes, so that the lasting confined single filament stabilizing the lateral grain and ensuring the relatively low threshold current. So there are three optical confinement methods used for bounding laser light in the lab. So with the help of optical sources we find the frequency spacing. So G of naught is the maximum gain proportional to the population inversion, sigma is the spectral width, lambda naught is the wavelength. So if we consider the frequency of wavelength spacing between the modes of multimode fiber, we use only longitudinal modes. So if we find the frequency spacing for the successive mode of frequency V m-1 and Vm, where m-1 m are the integer, so we can write the formula like this: m-1 is equal to 2ln divided by C V of m-1, or you can write it as m is equal to 2ln by C Vm. So two integers we are taking, m and m-1, so m minus m-1 is equal to 2ln by C Vm minus 2ln by C Vm minus 1. So if we subtract this, finally what we get is del lambda is equal to lambda square divided by 2ln. So this is the frequency spacing.